Hi, everyone. Welcome to tonight's Fiveable AP Physics 1 stream. Today, we're going to be taking a look at some combo problems for free response questions dealing with forces and kinematics. So the type of FRQs that merge the two units together. So coming up on our stream, oh, by the way, if you want to follow for more content, physics, calculus, whatever other AP subjects you're interested in learning about, go ahead and follow at ThinkFiveable on Twitter, Instagram, YouTube, or just check out fiveable.me. Okay, so with our intro, we are going to basically be looking at free response questions, especially that blend kinematics concepts, so projectile motion, free fall, accelerations, velocities, times, distances, that sort of stuff, with the forces problems that we've been working on for the past couple weeks or so, maybe a month or so, with Newton's laws and friction and ramps and stuff like that. Okay, we're going to go through some useful equations, just in case you've forgotten a lot of the stuff about kinematics, because at least for my students, it's been about a month since we really hammered into them, the XY tables and the how we solve projectile motion, that sort of thing like that. So we're going to go over those really quickly and then jump into some combo problems. There are 5 different problems we're going to look at, and the slides that will be linked with this will have all of them, as well as I'm going to solve them out on another, solve them out on a different camera in there too. So if you're watching this after the fact and want to see the questions before we get to them, go check out the slides attached to this presentation, and they'll all be listed in there eventually. If at any time you guys have any questions and want to throw out some comments, some feedback, concerns, that sort of stuff like that, please do so in the chat, and I will answer them as quickly as I can. Go through. All right, so useful stuff. So on your reference tables, you guys have these 5 equations. These are actually the first 5 in the mechanics section, and the first 3 of them deal with kinematics. So hopefully these are kind of familiar to you guys. Looking at V equals V naught plus AT, X equals, so for finding velocities, initial or final, given accelerations and times. The second equation, useful for finding distances. This is probably the #1 go-to equation for any sort of projectile motion. Finding the time an object takes to fall a given distance, or how far away from a cliff will a ball land when it's been thrown, et cetera, et cetera. And then V squared, V naught squared plus 2a delta x. This one's really useful if you don't know time and you want to do something without having to calculate time first in there. After we get through the 3 kinematics ones, we hit our 2 main dynamics ones, our 2 main forces equations. So we have A equals F net over M, Newton's second law in equation form, and then our friction equation 1. FF is less than or equal to mu Fn, where Fn is the normal force, mu is our coefficient of friction. Okay. So those 5 equations, knowing when to use them and plug them in and stuff like that is really important for us. And also the big thing that we're going to run into once we get into projectile motion sort of questions again, or even just in forces with angles, is to make sure we separate stuff out, that we're talking about X direction horizontally or vertically, and those are independent of each other. If it's on a ramp, it's parallel and perpendicular to the ramp are independent of each other. Those things, we got to make sure we separate out our forces and our velocities, accelerations, stuff like that into those components so we can actually compare and contrast what's going on there. Third big thing, forces stuff. I know we spent a while talking about forces already, but on horizontal surfaces, the downward force of gravity should equal the normal force going up, as long as we don't have any other angles or other stuff like that going on. That'll be useful when we're doing friction stuff as well. Of course, we've got Newton's 3. Balanced forces don't accelerate an object, law of inertia. We've got F equals ma. Unbalanced forces do cause accelerations, or accelerations are caused by unbalanced forces. And then the third law, the action-reaction pairs. A pushes on B, equal and opposite to B pushing on A. And finally, as just kind of a reminder, especially when we're doing about forces, we can look at single objects and the forces on that, or we can look at entire systems, multiple boxes together, or things like that. That may be more useful depending on the question, than looking at a single object to simplify things or just to get a big picture view. So for forces, we can look at big picture and look at systems, or we can look at individual objects. Depending on the question, we may want one or the other, may be a better way to solve that question. All right. So without further ado, let's dive into some of these questions. Okay. All these questions have been pulled from past AP exams or the AP Classroom through College Board. Some of these are fairly old, some of these are fairly new, but they all kind of give you an idea of what we're looking at for this sort of blending of stuff together. Oh, excuse me. So this one, first question, we have a student with mass M standing on a platform scale in an elevator in a tall building. Any positive direction we're looking at is going up. And we need to draw a free body diagram with forces. We need to figure out some expressions for accelerations in terms of other things or reading on the scale. We've got a graph to read, and we've got some other common things to do with it. All right, so let me switch over to the camera, and we will take a look at solving this question. All right, there we go. So let's make sure this is up and running. Hey, there it is. Okay. So we have a student standing on a platform scale in an elevator in a tall building. We're told positive is up. We want to draw a free body diagram. All right. So what does that look like? Well, we have a student standing on a scale. How many forces should be on this student? All right. So we should have, there's my student, we should have their weight going down, and we should have a normal force, or in this case, since all the questions are going to be referring to it as the reading of the scale, I'm just going to call it F scale. Yes, it is a normal force. You could do Fn or capital N or anything like that as well. But for this one, I'm just going to call it F scale, just to give us an idea of where we're going with this. All right. And because the student's just standing on the scale, they're not pushing it sideways any way whatsoever, there are no horizontal forces here, just simply up and down. Right? And yeah, that's about it. Realistically here too, you probably could have said because they're just standing on a scale and we don't know anything about acceleration and stuff, you might be able to make a claim about those being equal, but it's better not to until we actually know what's going on here. All right, so there's my part A, all done. Scale goes up, gravity goes down, and if they're just stationary or not accelerating, they're equal, but we don't know for sure yet. All right, so part B, derive an expression for the reading of the scale in terms of the acceleration A of the elevator, the mass M of the student, and fundamental constants. All right, so this looks like it's a forces sort of situation. We're looking for the reading on the scale. So I'm looking for F scale, and in terms of A, M, and anything else. Okay, so fundamental constants, in case you've forgotten, this means we can include things like I can do little g. I can do acceleration due to gravity. And that's probably the only fundamental constant we will deal with today. Other things we could do eventually in the future, big G, K for electrostatics. There's not a ton of them, but most of them are on your front page of your reference table. And those are the allowed fundamental constants for that. Okay, so anyway, for this part, we're going to start off with our wonderful Newton's laws, F equals ma. Now, why did I choose this one? Well, because we're talking about the reading of a scale, which is a force, and we have to use acceleration and mass. So this one just kind of makes sense. There's no friction involved here. I don't have to do FF equals mu Fn. And they're not mentioning anything about times or velocities or anything like that. So this is my go-to spot. All right, so some of the forces. I have two forces acting on my student. I have the scale going up and gravity going down. And because we're calling up positive, I'm going to do F scale minus the gravity has to equal m times a. So our upward force minus our downward force will equal our ma term. And if A is positive, that means this one's bigger. If A is negative, it means the weight is bigger. and we should be pretty good. So now we just have to do a little rearranging here. F scale equals MA plus MG. And I'm probably going to leave it as MA plus G just to make it a little bit simpler to do the math out and stuff like that. But really, leaving it at this point is also perfectly correct. It meets all of our requirements. Yeah. So leaving it here or simplifying more. Either one's good. I like simplifying it in this case just to make it easier to read and understand. Okay. So back to our question. An inspector provides the student with the following graph showing the acceleration on the elevator as a function of time. All right. Single I, during what time interval is the force exerted its maximum value? Okay, so when is the force exerted by the platform scale on the student the biggest value we can get to? All right, well, if we have our equation for part B, force on a scale is the mass times the sum of the acceleration and our acceleration due to gravity. We're looking for F to be the biggest when A is the biggest. So where is A the biggest here? We're looking at A being a maximum somewhere between 12 and 16 seconds. So during what time intervals is the force force on the student by the platform scale on the student the maximum value? Anywhere between 12 seconds and 16 seconds. Okay. Down here between 2 and 4, this would be the lowest the force would be because our downward force needs to be bigger. So this is our minimum value for the force. Here is our maximum value for the force, and then other places in there doing other things. Now, double I, calculate that magnitude for a 45 kilogram student. All right, so let's finish this. T equals 12 seconds to 16 seconds. Double I, basically, and this is super awesome if you get this as an AP question on your test, it's just saying, hey, plug in some values into this equation that we already have done. Okay, so the force on a scale must be equal to the mass. They told us the mass was a 45 kilogram student. So 45 kilograms times our acceleration. Well, our max acceleration looks like we are one tick above 1 and 1, 2, 3, 4, 5. So each one of these is 0.2. So that's 1.2 meters per second squared. So 1.2 meters per second squared plus g, which we're going to make nice and easy and call 10. You could use 9.8, but for any free response question, g equals 10 is more than acceptable. So we're going to take 45 and multiply it by 11.2. And when we do that, we'll come up with a number. Let's see, bigger than 450, somewhere around 500. 45, yeah, okay. So with my calculator here, this comes out to be 504 newtons. And there is my reading on the scale. A couple things to remember while you're doing these problems too. Sometimes AP will actually award you points for units. So make sure you're getting in the habit of putting in units to your numbers when appropriate. In this case, everything gets one. Once you plug that in once, you're okay, but make sure you have units on there just in case. Also, units can give you the clue of what you need to do here. I can add these two numbers together because they have the same units. If they didn't, I couldn't. And then newtons for the force on the end, just to make sure we're doing it well. All right, and the last part, part C. During what time interval is the speed of the elevator constant? Okay, when does our speed not change? Well, our speed does not change when our acceleration is 0. So where on here is our acceleration 0? Sorry, acceleration is 0. So we have 0 acceleration anywhere in the range right there. And we also have 0 acceleration in the range here. So for this part, we're picking out any place where this is 0. So that's 7, 8, 9, 10. So we can do 7 to 10 seconds. And we can also do 17 through 20. And there is that question. A little bit of graph reading with accelerations, so kinematic skills that we've done before, and then going through and doing this stuff there too. You could also see this question be taken a step further and ask, and I know this is not on here, but they could ask something like a part D, what is the speed of the elevator after a certain period of time? And remember, to find speed, this would be where we take and do the area under the curve. So we do like the area of this shape or this trapezoid, either breaking it up as a trapezoid or as a two triangles and a rectangle. So yeah, actually, let's do that. Let's continue. Let's do more kinematics here. So if I wanted to find the speed here, so I'm going to add that to my list here. D is speed equals question mark. And let's say at 7 seconds, since I already have that one there on here. So what I would do for this one, I would probably turn this into a rectangle and two triangles. And if, unlike me, you remember the equation for the area of a trapezoid, great, do that. That's a one-step solution, simpler. I always mess it up. It's one of those equations I can't remember very well, so I don't use it. I will instead do two triangles and a rectangle. So in this case, D, if I'm looking at the speed of this thing, fold this over so we have more space for it. There we go. So for part D, if I'm looking for the speed at 7 seconds, I would do that speed equals 1/2 base times height plus base times height of my second rectangle plus again 1/2 base times height for my third triangle here, or my second triangle, my third shape. So in this case, 2 seconds in, 2, 4, 6. So this is 1/2 of 2 seconds times negative 1.6 meters per second squared, plus base times height here. There's 2 more seconds, and we are at negative 1.6 plus 1/2 the base here, 2, 1, 2, 3. So 3 seconds there, times again a negative 1.6. And then we do the math out here. So 1/2 times 2 is 1. So this makes negative 1.6 minus a 3.2 minus, let's see, 3 times 1.6 is 4.8. Half of 4.8 is 2.4. So let's see, 16, that makes 40. So that means our velocity at 7 seconds is a negative, I just had it, lost it, 5, 6, 7, 7.2 meters per second, because that is the area under that section. Okay. Again, this was not in this question as the AP provided it, but very easily we could have seen something like that included in there, where it would be a velocity part in there too. All right, so that's the first question. Let's take a look at the next one. Okay. So again, all these questions are sitting in the slides that are attached to this presentation. So please, if you're, again, looking at this in the future, take a minute, skim ahead. Please pause the video, take some time to take a look and see what's going on there. All right, so second question. This, again, old AP question. This is probably from, I would guess, mid-90s, but either way, it works. Let's take a minute, read through it, and see how we're going to solve this question. All right, so important stuff to notice here. We've got this block that kind of gets thrown off the edge here. Something I'm noticing right away is this looks like some sort of projectile motion arc going down there, which means I'm thinking XY tables. I'm thinking breaking this up vertical, horizontal components. We also have a ton of masses going on and a ton of distances being labeled. So my guess is that these are all going to come into play at some point in time as being important for us to know in there. And do I have any other? Oh, nope. Back to yellow. And we got some masses here too that are going to be important as well. So looking at this, I've got lots of numbers going on here. Let's just start trying to quantify stuff going on. So I saw the projectile motion arc, which makes me think XY table. So I'm going to start there and say that I'm going to break this up in horizontal and vertical motion. If you guys haven't done an XY table before, basically all I'm going to do is take all the terms out of those first three kinematics equations and list them. And then we'll break it up as, is this a horizontal or a vertical thing that I know? So all the terms, so V naught, V, A, we'll call it a delta X, and a T. Those 5 things. This could also be X minus X naught. You could do a separate one for X or X naught. Either way there, that's your preference. I like doing it as the change because more often than not, that's what we're going to look at. But either way. All right, so what do I know on this question here? Well, I know projectile-wise, we get to ignore all friction, which means there is no acceleration horizontally when we are traveling through the air. I also know vertically, when we're traveling through the air, the acceleration of our falling object will be 10 meters per second squared going down. Again, that's little g on there. All right. I know the ball needs to fall 2.4 meters down. So there's a delta for me here, a change in height of 2.4 meters. And it lands 1.8 meters away from the bridge, or from the table. There we go. So 1.8 meters away. I also know that this is moving just sideways at the beginning. Like this ball is only moving sideways, which means when it leaves here, its velocity is strictly in the X direction. So there is no velocity in the beginning vertically. It's completely horizontal. Okay. All right. So what are we supposed to find here? Because that will give me some clues as to where to go from here. So we're supposed to find the speed of the ball. Speed of the ball just after the block hits the bumper and the ball leaves the cup. Okay, so that is a horizontal velocity that we're trying to find. They don't tell me anything about final velocities, so I'm going to kind of ignore that for right now. That's not needed to solve this question. But the other thing that we need here now is I have to find time. And time becomes my number one thing that I want to find here, because pretty much all of my kinematics equations, my x equals x naught, my v equals v naught plus at, those all need times. And while I do have the other equation in there, the v squared equals v naught squared plus 2a delta x, I don't know anything about the final speeds of my object. So I really can't use that one either. Okay, so it looks like for this part, doing part A, my first objective is to find the time. How long does it take for that object to hit the ground? Okay. So looking at what I know here, and again, 95% of the time, this is what you're going to be doing, is you're going to use your vertical information to figure it out. I know how far we fall. I know we weren't moving up and down at the beginning, and I've got an acceleration. So I'm going to do y equals y naught plus v naught yt plus 1/2 at squared. Okay. This is the x equation right off your reference tables. I'm changing it for y's just to remind myself that, hey, every number I plug in here has to be from the y column, not the x column. Okay. And some other things of note here. We're not starting anywhere special, and we're not moving up and down. So those can both disappear. Those are both zeros. So really, this is 1/2 gt squared. And just solving it for t before we plug in things, multiply by 2, divide by g, square root. 2y over g. So that means the time is the square root of 2 times 2.4 meters, all over 10 meters per second squared. And that gives us a time of approximately 0.69 seconds. And if we were stopping here, just as an experimental point, 2 decimal point values matches up nicely with 2 significant figures in all of our other numbers. Okay, but we're not done yet. Part A's goal was to help us find the speed of the ball. So I'm looking for Vx. I'm not looking for t. So let's do part 2 of this, and I actually want to find v naught x. To do that one, we're going to do the same equation. We're going to do our x equals x naught now. That's the same exact equation. I'm writing it as x's because I really want to remind myself. Now we're talking, well, excuse me. Now we're talking horizontally, which means I'm only pulling stuff from the x column. But I do know that I have a time here that I can pull from. Okay. So other stuff we need to know, I'm not starting anywhere special, and I don't have any acceleration. So those terms both disappear. So I get x equals v naught x times t, and that means v naught x is just the distance over the time, which is 1.8 meters over 0.69 seconds, which equals, let's call it about 2.6 meters per second, 2.59 something, but 2.6 is good enough for this. And there is our part A. Done. We have found the speed of the ball just after the block gets over. Vx equals 2.6 meters per second. All right. Part B. Calculate the acceleration of the block as it goes across the table. All right. So now I'm going to kind of ignore our XY table now because we are no longer talking about flying through the air. We're talking about on the table. So now we're over here on this section where I know that we reach our final speed of 2.6 meters per second. I also know our initial speed here was 0 on there, and we have a distance of 0.95 meters. Okay. Now there's a couple ways you can do this question, or you might think about doing this question. Maybe it's worth trying to do forces. Because let's face it, this is the forces unit. We've been doing F equals ma for weeks. The problem is I don't know all the m's. I've got this giant big M sitting here that I don't know what its value is. So when I try to do summing all the forces, sure, I can sum all the forces. This one with nothing else, the weight of the block here going downwards. But I don't know all the m's. So I really can't do F equals ma, which means we're back to kinematics again. And really, we've got a couple options here. We could do something like V equals V naught plus AT, but we don't know T. We could do D equals VIT plus 1/2 AT squared. We still don't know T, and we don't know A. So we have 2 unknowns in both those cases. Neither one's going to work great there. So the best way to do this is to use the kinematics equation that doesn't involve time. That's the v squared equals v naught squared plus 2a, and I'm going to write it as delta x. X minus x naught is how your reference tables write it. I like this one a little bit better, but that's just me. So we know that our initial velocity is 0. It says it was starting and released from rest. So this doesn't matter. So we can say v squared equals 2a delta x. I'm solving for a, so we can do v squared over 2 delta x is equal to our acceleration. And now we can plug in our final velocity we found was 2.6 meters per second. Quantity squared over 2 times how far did we travel? We traveled 0.95 meters. And if we crunch these numbers, we'll get our acceleration of roughly 3.56 meters per second squared. 3.6 is perfectly fine for that too. It's a reasonable number of stuff to go through. But there's our acceleration. Hardest part here is just realizing we can't do forces because we don't know all the masses, and we don't know time for this section. So choosing to do other ones to find the time and stuff like that probably could be done. It's just going to be annoying. Maybe like some average velocity and distance sort of stuff there, but that's way too much work when you've got an equation like this that lets you solve it in one step without time. Not that it's wrong. This is just a whole lot simpler. Okay. Next part C. Calculate the mass of the block. So now we get to find out what M is. That's good because that was a big stumbling block in how we could figure out how to do part B with forces. But now that we know A, we can actually do forces for this because now I know A and I know the net force and I can figure out the M's. Okay. So in this case, this is one case where we can make a choice. We can either choose to look at the single object, block M, or we can choose to look at the entire system. And in this case, looking at the entire system of those three objects linked together, the hanging mass, the ball and the launcher, and our block sitting there, makes this question a whole lot easier. Very, very much easier. So that's what we're going to do. We're going to look at all the forces total equals M times A. So all the external forces here, what forces could there be that are not included in my circled area? All right, so, well, let's see. I can draw in some forces here. I have gravity pulling down, so some sort of gravitational force on the little hanging weight makes it pull down. I don't have any friction, so there's nothing pushing backwards on there. So there's no force going backwards this way. I've got tension pulling up on the weight and tension pulling from the mass, but those forces are both caused by things inside my circle, which means they're internal forces. They're part of my system. They're not external. I'm not going to include them in my total external forces or some of the external stuff here. So the only thing that will be on my external forces side is the weight of this object, which will be 2.5 G on there. Now, the mass has to be the mass of everything in my system. So that'll be the mass of the hanging one plus the mass of my ball plus big M. So this will be 2.5 kilograms times 0.3 kilograms. Whoa, no. Adding 2.5 kilograms times G equals 2.5 kilograms plus 0.3 kilograms plus M all times A, which we found to be 3.56 meters per second squared. Okay, so we'll take 2.5 multiplied by 10, that's 25. So 25 equals 2.8 plus M all times 3.56. So we'll divide 3.56 over, subtract out 2.8, and I will get a mass approximately of 4.2 kilograms. And that is my big M value there. All right. Now, for the last one, part D. If I make the ball get heavier, the horizontal distance it travels will get smaller. A heavier object for this ball goes less far, less than 1.8. Why will this happen? Well, this is a good thing to ponder. We know that the ball travels through the air because it gets some final velocity. That final velocity comes from the acceleration of the ball as it gets pulled downwards. The bigger the acceleration, the bigger the velocity. The smaller the acceleration, the smaller the velocity. So in this case, we have F equals ma. The force here is a constant. It is always going to be 25 newtons, or 2.5 kilograms times g, unless we change that. So this is a constant 25 newtons, not changing as the block or as the ball changes. What does change is the mass. This mass we're going to make increase. Well, if we make the mass increase and the sum of the forces doesn't change, that means our acceleration must decrease. So increasing the mass with a constant force means a smaller acceleration. A smaller acceleration turns into a smaller velocity because you're traveling the same distance here. So a smaller velocity, and a smaller velocity turns into less distance. Okay. And now if this was your AP question, test or something like that, you'd want to do this in a paragraph or something like that. This is kind of the rough schematic, but you'd want to put this in nice words saying like, because the force or because the net force on the ball is a constant value that doesn't change with the mass of the ball, increasing the mass will cause the acceleration of the ball to decrease. The acceleration of the ball decreasing over the constant distance it travels, 0.95 meters, means that the ball will be traveling slower when it reaches the end of that. So the velocity will be less than the 2.6 meters per second we calculated in part A. Therefore, if the ball leaves the table with less horizontal velocity, the table height hasn't changed, so it will travel a shorter distance as well. Okay. Something like that in those words would be what you're looking for a free response sort of paragraph essay in here. For this one, they're probably looking for a few sentences. Something talking about the force being the same, mass goes up, A goes down, and then another sentence with if A goes down, V goes down, and if V goes down, distance drops. Something along those lines. All right, make sense? All right. Next one. Scrap paper out of the way. All right, next one. We're looking at a really old question, 1988 B1. We have a helicopter that holds a 70 kilogram package, suspended from a rope 5 meters long, accelerates upwards at 5.2 meters per second squared. All right, on the diagram below, draw and label all the forces acting on the package. All right, so this package suspended from a rope accelerates upwards. Let's draw some forces. So really, we have one force, that is gravity pulling down, and our second force would be a tension in the rope. And that's it. No sideways forces, no friction, no air resistance. We get to ignore all that stuff already. So we're not paying that any attention. So yeah, that's part A. One up, one down. We don't have to make them equal, or we don't have to make any claims about their equality or anything like that. We do know, since we're accelerating upwards, that the tension needs to be bigger than the weight going down, but they don't give us a nice scale to do that. So really, we're just kind of stuck with that's the way it looks. Okay, part B, determine the tension in the rope. Okay, so for part B, we're looking at the tension in the rope. Let me do this up here. So sum of the forces equals MA. And we know our two forces. We have tension going up minus the weight of the block going down. It has to equal M times A. T equals M. And I'm going to, again, combine them. A plus G. And in this case, we have all the numbers, so we can crunch those numbers. So this is 70 kilograms times 10 plus 5.2. So this is 15.2 meters per second squared, which means our tension in our rope is approximately 1,064 newtons. Okay. And there's part A, or sorry, part B done for us there. pretty good. Okay. Nice, simple Newton's law question. Nothing super crazy about that. Part C gets a little crazy. Part C says when the upward velocity of the helicopter is 30 meters per second, the rope gets cut. And the helicopter continues to accelerate upwards at 5.2 meters per second. Determine the distance between the helicopter and the package 2 seconds after the rope is cut. All right, so we're accelerating upwards, going faster, 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 and suddenly the rope stops getting cut. Helicopter goes up, package does something, and then we have to figure out the distance between those two things. All right, so this calls for some more paper. So I have my helicopter, and there's my helicopter as a nice dot. We've got our package, and then we are looking for the distance between them at 2 seconds later. Okay, well, let's try to break this down into some parts we can manage here. So first off, the helicopter will keep accelerating upwards at 5.2 meters per second squared. Okay. Yeah, so the helicopter's going to keep accelerating upwards. Oh, sorry. They also tell us in the question, there we go, that the helicopter is moving 30 meters per second up. So this means our V naught is 30 meters per second, also going up. Okay. The package, on the other hand, now doesn't have that tension going on. The only force acting on it is gravity. So the package will have an acceleration going down of 10 meters per second squared. Negative because down, and then still has that initial velocity of 30 meters per second going up. So basically what we need to do, we need to figure out how far up the helicopter rises, how far down our box falls, and then finally remember, and this is where this question is really sneaky, that we already started with a 5-meter rope between them. So we'll have to take the helicopter's distance, the package's distance, add them together, and then add 5 meters to it to get our total distance between the two. All right, so let's do it. So I'm going to start with the helicopter. Helicopters, we're looking for a distance, so I'm going to do y equals y naught plus v naught t plus 1/2 at squared. So for the helicopter, it has a V naught of 30 meters per second. It's going to continue for 2 seconds because that's the time we needed from this. And its acceleration is a positive 5.2 times 2 seconds squared. So for our helicopter, punching all that in, it has gone up 70.4 meters. So far, so good there for the helicopter. For the package, or our box, we're doing the same thing. So our package will have an initial velocity of 30 meters per second times 2 seconds plus 1/2 of negative 10 meters per second squared times 2 seconds squared. Okay, and if we crunch this, 60, 40, 20, that gives us a 40 meters for our distance. And now the crazy thing here, or maybe not that crazy when you think about it, this is a positive number, which means that our package actually went 40 meters above where we let it go. Now, does that surprise? Well, maybe not, because our velocity was really big. We're going up 30 meters per second. Our acceleration, gravity, only slows us down 10 meters per second every second. So we haven't even gotten to the point where we have turned around and started falling down with this package yet. It's still going up, and it's gone up 40 meters from where it started. Okay. So what do we have to do here? Let's figure out our total distance for this question then. So our distance will equal 5 because we started with 5 between them. That's the rope. Plus 70.4. This is the helicopter. then minus 40, this is the box. And if we do all that, let's see, 75.4 take away 40 is 35.4 meters between the two of them. All right, and there is part C. Pretty good. A lot of numbers here. This one, especially part C, very easy to get confused with looking at helicopter, looking at box, and forgetting the rope. I remember the first time I did this question, I completely forgot the rope and was wondering why we were so far off. But yeah, so you got the helicopter doing its own kinematics thing, the box doing its own kinematics thing, and then the rope in between them. So there's that one. Done and done. All right. And I think we got time. Yeah, we got 45 minutes in. Let's do 2 more questions, I think. And that way, when you're watching this later, we can take a look at all 5 of my examples in there. And again, all these old AP questions, definitely something that could show up on the exam in some form on there. All right, so we've been doing a lot of ones with numbers, with actual numbers, numerical calculations. 98B1 kind of flips that on the head because this one has no numbers. This is all about algebraic derivations. So lots of stuff to do here, but we have very few numbers to do this thing with, which honestly, if you haven't caught on by now, most of our AP1 questions, especially with this sort of thing, are going to be involving no numbers. So there you go. Think of it as like a continuation or a preview for where we're going here. All right, so for this one, 2 small blocks, both have the same mass connected by a string. The length is 4 times the height and no mass. Block A is put on tabletop and it's smooth. Smooth word here means we get to ignore friction, which is wonderful. Block B hangs over the table. Distance from the tabletop is 2h above the floor. B then gets released from rest. And we get to express all our algebraic answers in terms of H, M, and G. So just make sure we can't have any T's in there. We can't have any, I don't know where the letter could come up, but tensions, that sort of thing like that can't show up in our final answer. All right, so part A, determine the acceleration of block B as it descends. All right, so here's another great example of where we're looking at this whole thing as an entire system. Makes a lot of sense. If I treat both boxes as being one single object, we can say that there is only one force on them, and that is the force of gravity pulling that first mass down. So if I look at the total system again, all the objects in here, and do F equals ma, we're going to have mg, the weight of this block pulling down, has to equal 2m, the entire mass, times a. And we can then play my favorite part of math, crossing stuff out, divide by m's to get those gone, and I will get g over 2 equals a. And there is our total acceleration. Okay. Now, you could have done this also looking at block B and having mg going down and tension going up, and then block A having tension as your net force in there. Find the value of tension from block A and plug it into block B. But that's more work than I want to do right now when I can look at the entire system and make it simpler. Okay. Part B. Block B strikes the floor and does not bounce. Determine the time at which block B strikes the floor. All right, this one looks like kinematics. Block B is accelerating down with that acceleration, g over 2. And it has to fall a distance of h before it hits the ground, and it's released from rest. So our initial velocity here is 0. So I'm going to go to my standby projectile motion free fall equation, or my basic kinematics equation that I use for everything. I have to fall a height h. I don't have anything special. I'm not moving at the beginning. And my acceleration is g over 2. And I'm looking for t. So solving this times 2 times 2. So we're going to get, 4h over g equals t squared, which means t is the square root of 4h over g. Or if we really wanted to simplify, not that we needed to, but we can, it's also 2 square root of h over g. Not sure which one's going to be easier for going forward, but either one of those will be perfectly acceptable for that. Okay, so part C, describe the motion of block A from time t equals 0 until block B strikes the floor. All right, so for this one, block A gets pulled that away with a constant acceleration. And that's about all we can say here. So it will move with acceleration g over 2. Until t equals t1. So basically until block B hits the floor, block A just gets the same acceleration. They're connected with a rope. We've got that unbalanced force on B, so we're just going to go with it. Part D, what happens to the motion of block A from the time block B strikes the floor to the time block A leaves the table? Okay, so once B hits the floor, there's no more acceleration. There's no more pulling down here. So this must mean that A will have a constant velocity. And you know what? Let's calculate what that is. So we can do something like V equals V naught plus AT. V equals 0 plus G over 2 times T1. Oh, we know what T1 is. We know that the time here is 2 square roots of H over G. So V will be, let's see, the 2's cancel, G square root of H over G. That looks kind of strange. Which I suppose we can bring that in and simplify this as square root of GH. That looks a little better. So constant velocity, V equals the square root of GH while it's on the table. And finally, part E, determine the distance between the landing points of the 2 blocks. All right, so block B didn't go anywhere. Block A is going to land farther away. How far away? I don't know. We should figure that out. So block A, let's just reframe the question. Block A leaves the table, traveling this speed. It has to fall for a distance of 2h. How far away from the edge of the table is block A going to end up? Well, this looks like another projectile motion question. X, Y tables, all that fun stuff like that. So let's make an XY table. So for block A, X and Y. V naught, you guys can't see that. Let's move it up here. V naught, VA, distances and times. We are moving the square root of GH. I am not moving up and down. I don't know anything about those. 0 and G. I'm looking for that number, and I have to fall 2h worth of distance on there. And then, of course, T's, I don't know either. So just like in our previous questions where we had projectile motion, step 1, let's find the time. So we're going to find T. So Y equals Y naught plus V naught T plus 1/2 AT squared. 2H equals 1/2 GT squared. 4H, yeah, I can do math. 4H over G square rooted equals T. Hey, how about that? That's exactly the same time it took for block B to fall. But that makes sense because block B had to fall half as far with half the acceleration. Block A has to go twice as far with twice the acceleration. So that works. And, you know, if you saw that before I did, you just saved yourself some math, which is wonderful. And now we can find X. How far away did it land? This again is x equals x naught plus v naught t plus 1/2 at squared. X naught 0, a is 0. So x will be the square root of gh times the square root of 4h over g. The g's cancel. So I'm left with x equaling the square root of 4h squared, which is just 2h. And that is how far away our objects end up. And there is that question. All right. And the last one, I realize we're getting pretty close to the end of time here. So I'm just going to quickly run through this one again, just so you guys have it for what we need to do for this later on. Okay. This one is by far the most complicated of the ones we're doing today. But again, could show up. Viable AP question. This is fairly recent too, so we'll go with it. Block of mass M pulled along a rough horizontal surface, constant force F1 at an angle of theta, acceleration is A1. We've got to do everything with those symbols and fundamental constants. So free body diagram with all the forces. Gravity goes down. We've got this F1 going up that way. We've got some normal force going up. We've got some friction going back. Lots of forces to deal with there. All right. Part B, derive an expression for the normal force exerted on the surface by the block. All right, so part B, we are accelerating here, but I don't think it says we're accelerating up and down. So I feel pretty safe saying that our vertical forces all have to be 0. Okay, so where are my vertical forces coming from? They are coming from some vertical part of F1. Wow, there we go. Some vertical part of F1, as well as our normal force on there. And then they must all be canceled out by the weight of the block going down. So we're going to say Fn plus F1, we're looking opposite, so that's sine theta, must equal the weight of our block. So now we can say our normal force must be equal to mg minus F1 sine theta. And just checking m, F1, theta, and constants. Okay, so all the stuff in here is allowed with our restrictions. So there we go. That's part B. Part C, derive an expression for the coefficient of kinetic friction mu between the block and the surface. All right, so we got to find some mu here going on. So for this, mu only shows up in one equation. So I suppose we should do that one. Well, should we? Not yet. We're not going to jump into mu yet. Eventually, knowing mu here, I have to use FF equals mu Fn. But FF is part of the horizontal forces here. And I've got this acceleration thing floating around. So I'm probably going to start off by looking at the horizontal forces. Okay, this means that F1 cos theta going sideways minus the force of friction must equal m times a. A1, because that's the symbol we're using here. All right, that being said, let's simplify some stuff. F1 cos theta minus mu Fn equals ma1. Okay, there's my mu. I just got to get that by itself now. So let me add and subtract to get mu over to the right side here. So F1 cos theta minus ma1 equals mu Fn. Okay, great. So I'm allowed F1, I'm allowed theta, I'm allowed m and a1. I'm not allowed Fn yet. This is the one thing that is not allowed in my thing. So I'm going to plug in all the stuff we have over here. So F1 cos theta minus ma1 equals mu times mg minus F1 sine theta. And now it's just a matter of dividing all the stuff over the other side, and we'll get our final answer here. And here is where I'm leaving it. Could we have done more? Sure, we probably could figure out some way to do some math and make that work, but why? This is done. This is good enough for that. All right. Next part, part D. For the graphs, we need to sketch graphs of the speed and displacement. V and X are the blocks as functions of time. If the block started from rest at X equals 0, T equals 0. Okay, so we've got to figure out some graphs. Yay, graphs. All right, well, let's think about it. We have our acceleration here, A1, and A1 is a constant. We're talking about a constant applied force, F1, so A1 should be constant. If we have a constant acceleration, our velocity should increase at a constant rate. So this should be a constant positive slope. All right. And the last part is going to be our X displacement graph. Our displacement graph here, again, with a constant acceleration, should look like a parabola, an upwards or concave up facing parabola. And hopefully those make sense with your kinematic stuff as well. All right, well, thank you guys for tuning in. We're going to end the stream right here. Again, as you guys look through this in the future, all these questions are on the slides, so you can try them out before you come through and compare answers with me. Hopefully we all agree and I didn't make a mistake somewhere, but if I did, feel free to give me a shout out and let me know that I made some mistake or whatever like that. All right, I hope to see you guys in the future. For next week is circles, circular motion, gravitational forces, all sorts of fun stuff like that. So I hope to see you then. Have a great night.